Today, I'm not going to show any movies. I'm also going to report on a negative result, and I hope that's okay. That's science. Sometimes involves negative results. I'm going to be talking about realistic simulations of the intergalactic medium, the search for missing physics. And what I mean by missing physics is either known physics that we haven't included in our model, or maybe it's just new physics that none of us have thought about in this context. It's in the context of the intergalactic medium, which by volume far outweighs anything you're doing, but also by mass, including galaxies. The intergalactic medium has almost all the baryons produced in the Big Bang. So this is really the heavyweight subject. However, the IGM is rather difficult to observe. So this talk is about a research that is motivated by the comparison between models and observations at high levels of precision. And that's where the missing physics seems to be suggested. So the intergalactic medium is observable, however. If we are here and we have a bright source of radiation like a quasar, the path length intersects gigaparsecs of intergalactic space. And here you see a real spectrum, high-resolution spectrum from Keck or VLT. And this scribbledy-scrabbledy you see here is all data. It's called the Lyman alpha forest. Occasionally, this line of sight intersects the outskirts of a galaxy, and you get a very deep absorption feature called a DLA. But most of the path length is going through low-density intergalactic medium. And what is so interesting about this is the intergalactic medium is shaped by the cosmic web in the dark matter. And therefore, this spectrum is actually a probe of the dark matter distribution on enormous scales. And Rupert Croft, who's sitting back there, did some of the original foundational work to make the connection between hydrosimulations of the intergalactic medium and the dark matter power spectrum. And I would say we're still not done with that, right, Rupert? We're not done with that. Okay, well, about 20 years ago, 3 groups, one of which I was involved in, figured out what was causing the Lyman alpha forest. And that is this cosmic web, which you see in dark matter simulations. But these simulations included gas and included the photoionizing background that comes from the quasars that fill the universe with UV radiation. And so the idea is we're here on Earth, we're looking at a very distant quasar, and the line of sight intersects all of these filaments caused by the dark matter, but you're seeing neutral hydrogen in this mostly ionized intergalactic medium along the line of sight. Okay, so with this model in mind, one could go off and write dozens of papers trying to refine this picture and compare with data and so forth. So these are already over 20 years old. You see the dates here. This is observational data from my colleague David Teitler at UCSD. These are resolved absorbers. And these are all hydrogen Lyman alpha at different redshifts because of different distances along the line of sight. And this is a synthetic spectrum from one of my papers in 1997. And you see that the simulated spectra qualitatively resemble the observed spectra in terms of the number of lines per velocity interval, the depth of the lines, the width of the lines, and so forth. And so we were all euphoric 20 years ago. We've solved the problem. Let's go do something else. But science has a way of remaining interesting. What happened, of course, was we had bigger simulations, not just us, but other people working in the field. Here's a 1,000 cube simulation I did back in 2004. 3 actually, published it in 2005. It was the first 1,000 cube simulation, hydrodynamic cosmological simulation in a large box. Lots of papers were written trying to see how good the agreement with data could possibly be. And of course, the data is getting better. More data, more precise measurements. And interestingly enough, a small but persistent discrepancy emerged through these comparisons of simulation and observation. And I'm talking about comparisons at the few percent level. And so working with David Teitler over the years, we ruled out observational systematics as the source of the discrepancy. We did convergence studies on the standard model, which I'll define in a minute. Showed that converged simulations are still discrepant. Box size, of course, is important. The bigger the box, the more matter power. Long wave modes shape the intergalactic medium. We explored that. And so the talk I'm giving today is reporting on my just completed PRAC project with the title I started with. Looking at whether there is known physics that is not included in our model that might restore agreement. Known physics. This slide here is actually from my 2016 presentation in this very room where I didn't yet have the results. Today I'll report on the results. It may be that there's the fact that we don't have galaxies in our piece of the universe with dense neutral halos. Maybe that's the source of the problem, source of the disagreement. But I'll be talking about this today. Okay, so how do you quantify this discrepancy? As I said, it's at the few percent level. So if you just take this and just calculate the probability distribution function for the flux, which is the y-axis here. Just count up how many pixels are at different values of the flux. You get what's called the flux PDF. And so here is flux here. 1 means full transmission, complete transmission. 0 means full absorption. And this is just the normalized flux PDF. And the data is the red dots. And with error bars. With error bars. And you notice the error bars are very small. In fact, you can't even see them over here. And over here, where you're looking at the few rare strong absorbers, the error bars are still rather small. So if you look at the two colored lines, which are simulations of the standard model of the intergalactic medium that we did during this project, you see that we have too many low absorption lines compared to data, and we don't have enough high absorption lines compared to data. And then there are 2 simulations here screwing around with the strength of the intergalactic field, UV radiation field. And we've done a lot more screwing around than I'm showing here. And no matter what we did with the standard model, which basically has 2 knobs. One is the H1 photoionization rate at a given redshift. The other is an X factor due to helium reionization, photoheating effects. No matter what we did, we can't get this shape. Can't get that shape. Then along in 2008, Bolton and collaborators published a very interesting paper where they just said, forget about self-consistent hydro simulations. Let's just use what's called the equation state of the IGM. It's basically just the temperature versus density relation. Let's use that as a free function and screw around with the free function and see if we can improve agreement. And lo and behold, they found that an inverted temperature density relation in the IGM improves agreement. Now, the standard model would have temperature going up with density. And it's a power law. And it's a very, Nick Gnedden, I don't know, Nick, are you in the room? Nick wrote sort of the key paper explaining all that back in '97. So an inverted T-row relation has lower density gas is hotter, which is not at all the way an ideal gas that's photoionized, that's expanding or contracting, works. But here are these model comparisons. And indeed, these inverted or isothermal was actually better fit than the standard model. So that got me thinking, how could I do that with known physics? So what we did was go from this. So the standard model does the dark matter, does 6 species primordial gas chemistry in a UV background radiation field that is just the same everywhere. It's evolving with redshift, but it's the same everywhere. And this UV radiation comes from all the quasars in the universe that are emitting that UV radiation. So that's the standard model. What we did was we treated the quasars as point sources and did the radiative transfer, multi-frequency radiative transfer, which is the hard part, right? That's really time-consuming. But could you possibly obtain an isothermal or an inverted temperature-density relationship in that way? And without going into my physical thinking at the time, I thought it through and I thought it's possible. And it's fundamentally because behind an ionization front, you get a single temperature. And with hard UV spectra like quasars, you get not just an ionization front, but you get a pre-ionized region that is preheated to more or less constant number due to opacity effects. And so I thought, gee, you know, with these quasars going off and on and these broadened ionization zones and just non-equilibrium effects, maybe. Got to simulate it. So that's what we did. So we used the ENSO code, which is a hydrodynamic cosmology code. We augmented that with multigroup flux-limited diffusion radiative transfer. And I've got a slide on that, so I'll just leave it at that. And we ran these simulations where every 45 megayears, we looked at all the halos in the box and we plopped down quasars with, consistent with the observed luminosity function. We varied the power law index consistent with observations. And so here you see redshift time evolving to the right, redshift 4, 3.5, 2. And here you see the fraction of set doubly ionized helium, helium-3, and you see that there's multiple quasars in this box. And down here you see the temperature, and here you see these broad, flat, photoheated regions due to helium reionization. So this is fundamentally a helium reionization simulation, but with enough spatial resolution in the box so that we can do a decent hydrogen Lyman alpha forest analysis. So that's the range of scale challenge. Big enough box to have multiple quasars, fine enough resolution to resolve the Lyman alpha forest filaments. Okay, just a slide or two on GFLD. So you're basically solving a bunch of parabolic equations for the radiation energy density in group W. So you have this diffusion term, and then you've got some cosmological terms, and then you've got your sources and sinks of radiation. And in our case, we solved five groups to roughly describe the power law spectrum of the quasar. And we did this implicitly to avoid any, light travel Courant condition. So 5 fully implicit iterative solves on 1,000 cubed and 2,000 cubed meshes. Every time step, 5 groups, implicit. So this was done with the Hyper library, which is a scalable library. So why do you need this multi-frequency radiative transfer? I alluded to this before, but the point is the higher energy radiation penetrates further. The cross-section is lower, it penetrates further. And so as you look at the different energy groups, you see that the higher energy radiation goes farther. And then the photoheating is the sum of all of those fields doing their ionization at their particular rates and places, and you get these very broadened ionization fronts. You then shoot rays through the box, and you can wrap around because of periodic geometry, and you can calculate synthetic spectra for neutral hydrogen, H1. You can also calculate synthetic spectra for helium-2, but I'm not going to talk about that today. And what we did is we did a standard calculation, and we did 2 variants of the quasar model so that the lines of sight are going through identical structures. It's just that their ionization and thermal characteristics are different. So here it is at redshift 4, here it is at redshift 2. Here's the answer. Wake up, here's the answer. Does it improve agreement with data? So here is the Flux PDF at redshift 2, 2.5, 3. All 3 of these diagrams have observational data on them. Those are the red dots again. And although, you know, to a lot of us astrophysicists, this looks like excellent agreement. To David Teitler, this looks like horrible agreement because these curves actually don't pass through the error bars everywhere. You can see that here. Redshift 3, you see that the models, again, have too many high transmission lines and not enough low transmission lines. Okay, so, however, it's even worse if you look at this comparison through a different statistic called the flux power spectrum. Just take the spectrum, normalize it, Fourier transform it, square it, then you've got a flux power spectrum. Here is the data. Actually, this is 3 different data sets from 3 different authors. And here are the models. The blue line, again, is the standard model, the standard optically thin, homogeneous UV background model. And then there are 2 more lines here, which are 2 quasar models that differ only when we turn on the quasars. In this one, we turn on the quasars at redshift 5. Here, we turn on the quasars at redshift 7. And amazingly, the flux power spectrum in H1 is virtually unchanged, and it's quite a bit lower than data at the large wavelength, a large distance, low wave number end. Okay, so that is still discrepant, and all of this good computing really hasn't solved the problem. So I have 1 minute left. Good, this is my last slide. So in summary, we have carried out simulations of the Lyman alpha forest, modeling quasars as discrete point sources. Inhomogeneous helium-2 reionization and heating have a surprisingly small effect on the H1 observables compared to the standard model. Surprisingly small. Of course, the helium-2 Lyman alpha forest is bonkers, and that's a whole another paper that I'll write in 5 years, but at this rate. But anyway, on the hydrogen Lyman alpha forest, it has surprisingly small effect, and that's because once those bubbles have percolated, the IgM just relaxes to that standard result very quickly. Subtle and not so subtle discrepancies remain between the models and the observations, suggesting that there is still missing physics. And I'm just at the beginning of my new PRAC. which is part 2 of this with the same title, which is to do this with AMR to include, to best of our ability, resolved galaxy halos to get some of that high density absorption in there. But it might also be some new dark matter physics. And if you look at what people studying dwarf galaxies are doing, they're taking off the gloves with regard to dark matter properties. Self-interacting dark matter, fuzzy dark matter, all kinds of dark matter. And so we're going to try to rule out good old galaxies as the missing physics. And if that doesn't do it, then we'll have to get more radical. Thank you.